So today's lecture, we're going to finish section 3, computing arithmetic. We're going to go over 3 specific algorithms today. We're going to be going over sign multiplication. How do you take in 2 numbers and multiply them by taking advantage of addition and bit shifting. And also we're going to compare and contrast 2 sign division multiplication algorithms. The first one is called restoring division. And we'll explain specifically why it's called restoring. There's a restoring step at the end of the algorithm. And then there's non-restoring division. We're going to compare and contrast their runtimes. We're going to compare and contrast how they operate at each different step of the algorithm. And then we're going to compare and contrast the pros and cons of each one implementing at a hardware level. If we were doing a VHDL version of this, how would we actually do it? So, as a basic overview, there's 2 parts to the multiplication. There's the multiplicand and the multiplier. So if you have 8 times 9, if you recall from last class, I gave you this example. This one's 2 times 3. So the multiplicand is the first number, and the multiplier is the second number. So 8 times 9, multiplicand is first, 9 is the multiplier. You'll lose points on an exam if I say, give me 8 times 9, and you give me 9 times 8. The reason why is because you have to do what the coder tells you to do. The computer can't just mix things around. Eventually, at some point, you're reliant on the coder, right? So you have to do what the coder, in this case, your professor, gives you in the assignment. So you lose points if you don't give me in the specific one I want. You have to understand. And the reason why, it's not just because you have to do it that way. Understanding the difference between multiplier and multiplicand is important to the algorithm. So doing it that way shows you understand the physical implementation. So what's going on here is we have our typical 32-bit arithmetic logic unit, and the multiplicand is the initial 32-bit input. And so your multiplier is the least significant bit of this initial product register. And what's going to happen is it's going to be put in initially to your 32-bit ALU, and then the result is going to be the first 32 bits of your 64-bit product register. Now what's going to happen is it's going to be shifting right. So if you think of it the same way as all the chalk is slowly running away. If you think of it, let's say we were doing 25 times 14, right? And we're doing it in a conventional manner. The first thing we would do is we would take the least significant bit and multiply it by our multiplicand, right? So it becomes 0, carry bit, even though it's in decimal. 4 times 2 is 8, plus 2 is 10, so this becomes 100, right? So now, what's going to happen is, you're going to do through your next iteration, where you're going to shift the numbers, and then do it again, right? So if you recall, in elementary school, middle school, wherever you learn this, you put a 0 here, and then continue doing that. So then you get 1, 5, 1 times 2, and it becomes 350. Now, this step here, this addition step, is what's going on in the product register. You're updating the product register by initially having 100, and then adding 250, or you're adding 25 bit shifted to the number. So we're going to be doing the same thing in the sign multiplication in the physical level. So here this point is we're testing for the least significant bit 32 times. That becomes an important part. If it's 1, we add. If it's 0, we do nothing. Because 0 times anything is 0. 1 time. So if it's binary, kind of a handwritten, so if it's 101 base 2 times 010 base 2, right? 0 is just 0, right? So that's 3 bits of 0. And then bit shift. And then 101, right? And then bit shift again, and this becomes 0. So this becomes 0, 1, 0, 1, 0, base 2. So what we're doing is you're adding this with the appropriate bit shift. So that's where this shifting right and testing the least significant bit, because let me do this example again. 101 times 010, right? So what's happening is you have your multiplier and your multiplicand. So 101 is here. This is what's in the initial bit right here, correct? On the one on the right, if you're watching this on the video later. And then initially what's coming around is 0, 0. Your 0 bit, right? So it's comparing, it's testing this least significant bit here. It's 0. Should I add? Nah, just add 0, right? So then my initial product register is going to say 0, 0, 0. Then I shift the multiplicand right, so the multiplier right. So now it becomes 0, 1, 0, 0, 1, right? And now it's going to test the least significant bit. Oh, it's a 1 this time. But now I've shifted this way on the register, so now it becomes, add this, 1, 0, 1. And you can see as you're shifting it, you're going to be shifting it, you're going to do this 32 times. Which is why we require a 64-bit product register. Because you have the initial 32 bits, and then we're going to be left shifting every time. And then that 64th bit is our sign bit. And so this is how we implement multiplication at this level. Now, I added a little note here, kind of just as a, for those of you who are taking algorithms and are familiar with or planning on taking algorithms. There's the fastest known multiplication algorithm is the Karastruba algorithm, which divides two n-bit numbers, and it takes it and then multiplies them together in n of log 2 base 3, or approximately big O of n to the 1.585. It uses recursive divide and conquer approach. So it's dividing it in half, then multiplying, dividing it, and think of it like a basketball tournament for those of you who are not familiar with that kind of divide and conquer approach. However, it is very, very, very difficult to implement in hardware. It's prohibitively difficult, which means is that in order to do this, it requires an insane amount of hardware where you're having to multiply the number of bits. If you're doing it 32, you have to do 2 bits, 32 bits, and then 2 bits, and then 4 bits, and 8 bits, and you have to recurse down and then recurse back up. So it's fast, but requires a lot of hardware. So if most designers wouldn't want to do this in hardware. So what we're going to be doing is doing kind of an implementation of this instead. So the sign multiplication, I have it listed here as another issue. Performing the algorithm with n iterations would overwrite the sign bit. Therefore, the algorithm is similar, but for n-bit multiplication requires n plus 1 bits of space. So that's where talking about what I was mentioning before earlier, the 64-bit. You start with 32, but shift it, perform the operation 32 times. You're ensuring that that last bit doesn't get hit. Because it's 0, 1, so it becomes 31 shifted over, then you have that excess bit. So here's the actual algorithm. Let me scroll down so that way the students in the back can see. So here's what's going on. You have your multiplier and your multiplicand. So your multiplier is going to be n plus 1 bits. On the exam, let me make a note here. On exam, you can expect n equals 4. So your range is going to be from 1111 all the way down to 0000. And so what is 1111 in 4-bit signed binary? No, why is it not 15? Yeah, that's why I'm asking, because I want you guys to be clear. Correct. So we take the 2's complement, 0, 0, 0, 0, 0, right? Switch all the bits, and then what do we do next? Add 1. So it's -1. It's not -7, but then that would be if you did this. So let's find out what is negative 7. So if we have 0, 1, 1, 1, right? Because you guys are going to be asked to do this binary conversion on the exam. So it's a good thing to practice. So what is negative 7? Just do the same thing, right? So here, tell me what do we do? Yeah. So how do we? So it becomes 1, 0, 0, 0, right? And add 1. So you put in 1, 0, 0, 1, right? Now the reason here we have n plus 1 is so that way, if you have a 4-bit value, it's actually going to have 5 bits here. So now you're going to account for that in your actual algorithm. So all this plus 1 gibberish, that's accounting for signs. So first one, we have product 2n. What does that mean? When I say product of 2n, there, that's array representation. I know some of you haven't had coding experience, so I want to make sure you guys understand what I'm talking about. When I say I have an array that can't be seen because of random pop-ups, if I have an array of 2n plus 1, that's the size of it, right? 2n plus 1. So let's say n is equal to 4. How big is my array going to be? 9, right? And I say product of 2n. So what does that value equal? 8. So it's p of 8. What does that mean, p of 8? What's that? No. No, the array is p of 2n plus 1, right? Is the size of it. So this is the inputs. I have a size array of 9. Now here, when I'm saying product of 2 of n, I'm actually accessing a specific element in the array. So it's the 8th element, right? But what is specifically unique about when I say 2 to the n? What is the first element of the array listed as? 0, right? So if I have 2 of n plus 1, and I'm saying product 2 of n, which element am I talking about? Of any, don't just say 2 of n. What is 2 of n? What's that?
The second one.
No. That's what I'm trying to address. I don't want you guys making that concept error on the exam. Not the second last element. It's 2n plus 1, and my first 0, 1, 2n minus 1, 2 of n, right? Because this is 0, is the first bit, right? So if I have 2 of n in here like this, this means I'm talking about the most significant bit. You understand? So if I had 3n plus 1 and I had 3n, what am I talking about here? The most significant bit. Right? So the most significant bit of your product, and what is the product? What's that? No, if I'm any multiplication problem. That is the result, correct. I just want to make sure you guys understand the wording. So the most significant bit of my result, the first thing I do is I'm going to XOR, if I have this, the multiplier is n plus 1 bits, right? So if it's n, what does that mean? Most significant bit of the multiplier. And if I have a multiplicand of 2n plus 1 and I say 2n here, what does that mean? Bingo. So this step, what we're actually saying is MSB of product is equal to XOR of MSB multiplier and multiplicand. So before you do anything else, right, you're saying, so what this is basically saying is if I have negative 8 times 9, before I say anything else, I'm initializing that my answer is going to be negative. Now, if you recall, I mentioned that this goes n plus 1 times, right, in the algorithm? So what this means is from 0 to n, this means n plus 1 times, right? Now we're testing that least significant bit, which is 0, right? Test LSB. And if it's 1, we're going to do just like I wrote up on the chalkboard. We're going to add it. So what are we going to do if it's 0? Yeah, physically you're adding 0, but when you're doing it on the exam, you're just going to do nothing, right? Because you're not adding anything. So the notation for some of you have said you haven't really dealt with algorithm notation. So you wouldn't have to do this in the write-up, else multiplier 1, 0 equals 1 equals 0, and then, or do nothing. If you're not doing anything, you don't have to add that in there, right? So that's why you're not going to have that in there. So that's why it's not included. So then what we're going to do is we're going to shift the multiplicand left 1 bit, and then we're going to shift the multiplier 1 bit. Now this is indented, which means no matter what you do in here, you're going to do this every stage of the algorithm. Okay. And then return product. So when you're doing an algorithm statement, you have to say what your inputs are, and then what you're going to send out. Now, before we do the questions, does anybody have any? I'm sorry, yeah, because we're going to do 2 example questions next. Does anybody have any question about notation, wording, what I mean by in certain steps? So I'd be happy to go over this again. I understand it's going to be a complicated thing to see on the first try. Yes?
Could you go over that product, the 2n thing one more time?
Sure. Okay, so let's say I have an array. And this is actually important because when we get to load and store in the actual data path, understanding how the numbering of arrays is important. So you have an array. And let's say 1, 2, 3, 4. We have 6 elements in this array, right? So in this case, it's just n equals 6 is its length, right? So if you're initializing an array, if you're dealing in C, C++, Java, you initialize it by saying, let's call it an integer array, right? In array A of 6. And there's all kinds of other things you need to do, but for simplicity's sake, I'm just going to say this. Because in array A of 6, 6 corresponds to the length. So in this initializing line of code, n plus 1, so for example, the reason why I have it this way, on an exam, you're going to be limited to 4 due to time, right? In MIPS architecture, you'd be doing for your final project, if you wanted to implement a multiplier, 8-bit, that becomes 17, right? 32 bits, implementing the full MIPS architecture, 32, 64, 65 bits. Make sense? But now back to our 6 array. The way they are numbered is this. 0, 1, 2, 3, 4, 5. So the most significant bit, the actual, if you want to say A of 5 is equal to 10, you'd be setting this number, A of 5 is the pointer to the location in the array, and the actual value is 10. Now, what if I did this? What if I said A of 6 is equal to 10? What's going to happen? Okay, so you do get an error. That is correct. What is physically causing that error? Bingo. So you have your location of your array is pointing here and here, right? So your compiler saying, if you're going to initialize this array, you have to go to one of these locations. what you're physically doing, what you're attempting to do is you're physically attempting to take these next 32 bits in the data memory and write 10 here. But that's allocated to something else. In fact, for those of you who may be interested in software security, there's a specific type of attack called a smash attack or buffer overflow, where the idea is you have a stack pointer and a heap pointer here. So you have this portion of your code, and you have some memory below and above it. And you have a stack pointer and a heap pointer, and all this indicates where the code starts and how much code you have. And in type of attack, they will do something like this, where they'll actually initialize a load store, load operation, where they're loading information here. So they smash your stack and heap pointer, so that way you can't access your code. So it destroys your ability to access certain parts of the computer. So that's why making sure that you have appropriate load and store operations and understanding array operations is important. Because not only do you want to ensure that you're able to access your data, but you don't want to destroy the integrity of the rest of the computer. So that's why understanding these notations is important. Any other questions? Okay. So the first one we're going to do is example 3.7. Multiply 8 times negative 9 using signed multiplication. So in this case, if we recall, I'm limiting it to n equals 4. Therefore, my multiplier is n plus 1 bits, right? Therefore, it's 5 bits. Correct? So what's my multiplier and what's my multiplicand in 8 times negative 9? 8 is the multiplicand, that is correct. And the multiplier is negative 9. So what happens is we're going to take the 2's complement of 9. So that becomes 0, 1, 1, 0. We add 1, this becomes 0, 1, 1, 1, right? And then the most significant bit becomes 1 here. Therefore, you get 1, 0, 1, 1, 1. So this multiplier, this is n plus 1 bits, as we stated in the algorithm. And we now have it in 2's complement. So from here, it's just the same thing as keeping this here. So recall, what was the first step of the algorithm? Before you do the iterations, before you do any bit shifting, what was the first thing we did? The sign, right? So this step 0, initialize, that's our XOR step. So here we're XORing this bit and this bit and updating the product. So here, the red that I have there, 1 XOR 0 is 1. So if I have 1 and 1 and I XOR them, what am I going to get? And why is that the result we want? Exactly right. Okay, so the first step is to test the least significant multiplier 0. You can put it like this, however you like, just as long as you indicate you know what you're doing. Testing the 0 bit of the multiplier. What's this value here? 1. So what does that mean we're going to do? Add it, correct. So here, the next step, 1.2. So when I say 1.1, 1.2, 1.3, 1.4, this is the iteration. Just recall, we have how many iterations? N plus 1, right? 0 to n means n plus 1 times. Therefore, since it's 4 bits, I have 1, 2, 3, 4, 5 iterations, right? So let me scroll back up so the students in the back can see. So I test the least significant bit. It is 1. Therefore, we're going to add the multiplicand to the product. So if you see here, I've added this to this. So now instead of just 0, 0, 0, this becomes 0.0000100. And as a hint,
What did you add it to?
I add it to the product. You add the multiplicand to the product. So this plus this was stored back into the product. So to go back to my document, we're taking the multiplicand, we're taking this, adding it and putting it back in the product register. So then, every iteration we shift the multiplicand left. So you see here, this 1 bit becomes here, right? So we're shifting it left, and then we're shifting the multiplier right. So we maintain the sign because we started out negative. So now we're going to be 1. We shift right, and it becomes, see that all the rest of these are shifting? So this should be, make that red. So here's a little thing to note. Control D. I'm not going to expect you to write these all. You see how a lot of these just stay the same every time? I do want you to indicate the first one, and then until it changes, you can just leave the next cell blank. So I understand that takes, or just do little quotations. So for example, here you initialize them, you test the multiplier, so you could just do that like that until it shifts. Right? You can do the same thing. Or you can leave it blank. Whatever makes you feel more. Some people like to do this just because they found that it's easier for them to keep track of what they did and where things changed. So if you get down and see I did a little test of the actual number here. Sometimes you get down to the end, you'll test your number, it's nothing close to what you expected. So then you can use that to figure out where you made your mistake. So in the meantime, we've shifted our multiplier right. We've maintained the bits here. The reality is we're just going to test these 4 numbers. So the numbers we put in past this are irrelevant. I find it's a good idea to keep that as a 1. In the next problem, we're going to do negative 8 times 9. So the 9 is a 0. So I'm shifting zeros instead of 1s. So now we test the least significant bit of the multiplier. It is a 1 again. So now we're going to add it. So you see here we've added it and it becomes 1, 1. Yeah, see this is same thing. You can do that, right? Does that make sense? You tested it, you add the multiplier, and then you get the new result. Again, we shift the multiplicand left, so you see this 1 bit is shifted here, and everything remains 0. Shift right multiplier, we see how it's shifting right again. Next, again, we test the least significant bit, and then since it's a 1, what do? See a lot of people going, add, and they're afraid. Add, right? Add it. So now, since we have this bit shifted again, we have this value, right? Shift left multiplicand, shift right multiplier. So we test it again. Look at that. What's that value? 0. Let me scroll up for those of you who can't see in the back. So what do? Nothing. Oh, you guys like doing nothing more than something. Okay. So then you just shift left again. This is a mistake I've somehow forgotten to update again. Oh, yeah. Zero. Okay, so now we've shift left again. and then shift right multiplier. We got a 1 again. We add this nut value. Shift left multiplier and shift right multiplier. Where what?
We at 4.1 we have the
Yeah, we're testing the least significant bit, right?
do nothing.
So you see how the previous one we were adding because it was a 1, right? Here, since it's a 0, we don't add. So instead of adding, we just go straight to the shifting.
How did it go? How does the multiplier go from 1 1 1 0 to 1 0 1 1?
Oh, because these should be saying these should be 0. Right? So there. So now we've shifted multiplier right. It's now a 0. So then we don't add because it's 0, and then we just shift left and shift right again.
So that
What was that?
what would
Thinking out loud? Okay.
with that one where you got the cursor at right now, I guess, would that be 1 1 1 0 and then on the shift
1 1 1 0.
and then it shouldn't still have 0 on the next one?
No. Why not?
Because we haven't shift right yet.
Here.
Right there we shift right.
Well, there you can do with this.
Yeah, you can do that.
So if you take the 2's complement of this, you'll come out to this number here, which is 72. So what we got is negative 72, which 8 times negative 9 is negative 72. So that's how we checked our answer.
I understand all that. The one thing I didn't understand was how do we know 8 was the multiple and? Is that right?
Multiplicand?
Yeah, multiple can.
Yeah.
How do we know that one was the 8?
The multiplier is the second value. 8 times negative 9. The multiplicand is the number you are multiplying, and the multiplier is the number of times you are multiplying. So if you're doing 8 times negative 9, it becomes 8, negative 8, yeah, right? Negative 8 plus negative 8 plus negative 8 plus negative 8. So that's the number you're that's the multiplicand. So the multiplier is the verb. What are you doing to it? Not bringing English into this course. Okay, so doing the same thing with 8 times negative 9. Negative 8 times 9. Since the multiplicand is negative 8, we're going to take the 2's complement, right? And so we're going to do sign extension. I'm sorry, this is, yeah. So initialize it. Multiplier is 9. Here's the funny thing about 8. Becomes 0, 1, 1, 1. When you add it, what happens? 1, 1, 0, 0, 0, right? So the positive and negative value of 8 in this case is the same, and the way you tell the difference is that added sign bit. So if this is 0, this would be positive 8, negative 8. And that becomes important to know as we come along. You're going to see these kind of add up and come out the same way. So here we initialize it. We do this XORing. 0 XOR 1 is 1. Same thing, we test the multiplier. Most significant bit is 1. So we add it. Shift left multiplicand. Shift right multiplier. So this one comes here, this one goes away. Then we test the least significant bit of the multiplier. It is 0, so we leave it alone. Shift left multiplicand. Shift right multiplier. As you can see, this is shifting here. Test the least significant bit, it's a 0. So you do what you guys like to do. Don't do much here. We just shift left and shift right. So here we're shifting left again. And then we're shifting right. Here it's a 1, so we're going to add this value to the product. We add them, we get this value. And that matches what we got before. So the thing is, when you add 0, when it's a positive, it's going to leave it alone. So that's where the making sure that you add the last iteration comes in. But here, we add, and then we get shift left multiplicand. So here we have it left shifted, then we shift right the multiplier. Least significant bit is 0, so we do not add. Shift left and shift right. And then this is our result, which matches our previous result. So negative 8 times 9 is the same as 8 times negative 9. Okay. Does anybody have any further questions on sign multiplication before we go to sign division? Okay. And nobody's asleep, so that's good. Okay, so I'm always paranoid that I've put in the wrong thing. Yeah. Yep. Let's pop off as 1. Yeah, there we go. That's the one right there. Okay, so we have 2 algorithms that we're going to compare. The first one is called restoring division. And so dividend and divisor, going back to what we were talking about here, Thomas, which one of these is a verb? Dividend or divisor? Divisor, right? I am the divisor. So if I'm doing 8 divided by 4, which one's my dividend and which one's my divisor? Dividend is 8 and divisor is 4. How many times am I dividing the dividend? The dividend is how many things I'm splitting it up into. Yes. Now I have 2 pieces in each dividend, each product, each quotient. So here's how we do this. A remainder, we're going to have a quotient and remainder. So if you recall from basic math, we did 8 divided by 3. This is equal to 2, remainder 2, right? So this is our dividend is 8. Our divisor is 3. Our quotient is 2. Let me pick a different example. Let me do 10 divided by 3. So that way the quotient and the remainder aren't the same. 3 remainder 1. So 10 divided by 3 is the result of 3 remainder 1. Dividend, 10. Divisor, 3. Quotient is 3. Remainder of 1. So the first step of the algorithm, we set, again, it's going to be 4, so it's n plus 1 bits. How many bits are going to be in my remainder? It's going to be 4 on your exam. How big is it going to be? 5, right? So I'm going to set the quotient equal to the dividend. I have a dividend of n bits here, so to make the notation correct, I'm going to have an n-bit quotient. Right, this is pseudocode. And so it's going to be equal to this value. So your dividend, so if we're doing 10 divided by 3, we're going to initialize the quotient to equal 10. And if you think about it, that makes sense. Because I want to have my initial value, and then we're going to keep dividing it by subtraction, right? And so we have this value called the mantissa here, which is different than the IEEE 754 format. And we're going to call that our divisor. So it's an n plus 1 bit representation of that. So we initialize that to equal our divisor. So down here we have 8 divided by 3 as an example. So our remainder is going to be initialized to 0. So in this case, since it's n is equal to 4, therefore it's going to be 1, 2, 3, 4, 5, right? Initialize the quotient is equal to dividend. The dividend is 8, so it'd be 1, 0, 0, 0, since it's n bits. The mantissa is going to be n plus 1. And that's going to be 3. So that'd be 0, 0, 0, 1, 1. So that's where that comes in. And so what's going to happen every iteration? So when I say I is 0 to n minus 1, and I have 4 bits, how many iterations am I going to do? If I have 4 bits in my architecture, right, and I say 0 to n minus 1, how many loops am I doing? 4, correct. So before in the sign multiplication, we had to add a 5th one to account for this. But in this algorithm, we don't have to, because it works out. So we have n minus 1. And the reason why is because of this restoring step that we do every time. So we're going to left shift the remainder, and the most significant bit of the quotient is going to become the least significant bit of the remainder. So here's what I mean. So remember we have this initial 1, 2, 3, 4, 5, right? And then what's my quotient at this point? If it's 8 times 3, it's going to be 1, 0, 0, 0, right? That's how we initialize these. So what's going to happen is I'm going to left shift the remainder. So this 0 goes away. And then the most significant bit of the quotient, which is this value, it pops off and becomes the least significant bit of the remainder. And we're going to go over step by step to explain this. But that's the basic idea of how it works. And then every iteration of the algorithm, we subtract the mantissa. So this becomes 0, 0, 0, 0, 1 minus, let's see, it was minus 3, right? So it's the 2's complement of 0, 0, 0, 1, 1. So this becomes 1, 1, 1, 0, 1. So that just becomes plus that, right? So when we say subtract, this becomes minus the value. Then left shift the quotient, and the most significant bit of the remainder is now the least significant bit of the quotient. So now what's going to happen is we're going to have the result, and that left shifting value, that value that pops off, is going to go to the end of the quotient, because we had that 4-bit quotient initially, right? And we popped off the most significant bit, so we only had 3 left, right? And then we're going to do the subtraction, and then we're going to take that most significant bit of the result, and we're going to append it to the end of the quotient. So now we have that result. So that's how we maintain the 4 bits there. So we're going to do that 4 times. Now, this step here is why we call this restoring division. If the most significant bit of the remainder at this point is 1, meaning that we've popped off as a 1, we add it back. So here, we're restoring the remainder to its initial value. So before we were subtracting from it, right? But if the most significant bit is a 1, then we're just going to add the mantissa back. So if it's 1 minus 3, right, it's going to be negative 2. And if we have to restore it, then it just becomes 1 again, right? 1 minus 2 plus 2 is 1. And then we return the quotient and the remainder just like we did in our other little example here. So here's 8 divided by 3 in restoring division. So let's go step by step through here to explain the algorithm. So like I said before, we initialize the remainder, the n plus 1 bits, as 0. The quotient becomes the same as the divisor. I'm sorry, the dividend. So that's 8. So we get that there. The mantissa is n plus 1 bits, and it's 3, right? Now, it's a very good idea to get the 2's complement of the mantissa, because you're going to be subtracting the mantissa every iteration. So the 2's complement of 0, 0, 0, 1, 1 becomes 1, 1, 1, 0, 1. Now, first cycle. Initially, here's how I got this number. So we had 0, 0, 0, 0, 0, and my quotient is equal to 1, 0, 0, 0, right? Like we have here. So the most significant bit of the quotient, so we left shift this value, so this goes away, right? And then the most significant bit of the quotient pops off of here and becomes the least significant bit of the remainder. So that's how I got 0, 0, 0, 0, 1 there. Does that make sense how I did that? Because for both restoring and non-restoring, you're going to be doing that step every time. So if that doesn't make sense, please ask. Okay. Subtract the mantissa, which is the same as adding 1, 1, 0, 1. We get 1, 1, 1, 1, 0. So then here's what happens. We take is the negative. Let me change that. Okay, negation. So here's what happens. We have this value here now, right? So that's where we left shift the quotient, and the most significant bit of the remainder is the negation of the least significant bit of the quotient. So we have 1 here. This means that we're going to change this value to 0. So what I would do when I took this class was I would do this. I'd draw a little arrow here, and I'd have a little negative along the arrow just to remind myself. So 1, and then this value becomes 0. So now we have 0, 0, 0, 0, 0 here. And then since the initial bit here was 1, we restore. So now we add 3. And here's the thing. On the exam, don't go through the trouble of trying to do this, because this is where students make mistakes. If you're subtracting, in this case, we're subtracting 3 and then adding 3, right? So what's the value going to be? It's going to be 1, right? So it's going to match this value every time. So that's cycle 1. So to get the number here, we initially had 0, 0, 0, 0, 1. So we had this value. Pop this value off. Right? And then we left shift the value, so the most significant bit of the quotient becomes the least significant bit of the remainder, and that's how we get 0, 0, 0, 1, 0. Subtract the mantissa every iteration. Again, here we get 1, 1, 1, 1, 1. The most significant bit is 1, so what does that mean? What are we going to do here? Bingo. The least significant bit of the quotient becomes 0. We negate this value and put it here. And then it's a 1, so what do we do in the next step? Restore. This is the restoring step, right? So then this number just matches this number. So cycle 3, we do the same thing. We have this value here. The most significant bit here becomes the least significant bit here. So now we have 0, 0, 0, 1, 0. We left shifted by 1, so that's where we initially had this, right? So we pop the 0 off. They take this value here and put it here. So now we subtract, and lo and behold, we have the 0 as the most significant bit. So what does that mean? Yeah, we negate the most significant bit here, and that becomes the least significant bit of the quotient. So now it's a 1, right? But here's the thing. Because it's a 0, we do not restore. You understand? And then last step, left shift, most significant bit of the quotient becomes the least significant bit of the remainder. So now we've left shifted the quotient here as well. So this becomes $ quotient equals 0, 0, 1 blank. Some sort of subtract the mantissa. This becomes a 1. So this means our least significant bit becomes a 0, like we see here.
and then we restore. And that's our result. So now our quotient is 2, and our remainder is 2. And since we're doing 8 divided by 3, the result was 2 remainder of 2, right? So, therefore, we've retained the right answer.
So on a test, it's going to be 4 bits. Is only always going to be 4 cycles?
Yes. Any other questions about this? Yes.
For like cycle 1 and cycle 2,
Mhm.
for the where you got the 0 in red,
Yeah.
where did how
Okay,
did you get
good. This is a good question. All right, so I want to make sure you guys understand this.
So, we take the most significant, after we subtract the mantissa, right? We take the most significant bit of the result here, negate this bit, and append that to the quotient. So here it's a 1, so what does this mean our bit's going to be? 0, right? So it's cycle 2, but since it's also a 1, we add the mantissa again to restore it. Cycle 2,
We left shift.
the left shift, we take the most significant bit of the quotient, pop it to the least significant bit of the remainder, subtract the mantissa, 1, 1, 1, 0, 1, this becomes 1, 1, 1, 1, 1. Most significant bit is 1, so what does this mean? There's 2 things if it's 1. What's that? Negate it and becomes what? Least significant of the quotient. And add the mantissa, correct. Cycle 3.
Again,
We left shift, so we had 0, 0, 0, 1, 0. So now we left shift 1, 1, 0, 1, 1, 0, 1, 0, 0, 1, 0. Take the most significant bit from the quotient, comes here. So it becomes 0, 0, 1, 0, 0. So subtract the mantissa, which becomes 1, 1, 1, 0, 1. So our result is 0, 0, 0, 0, 1. What is the fact that the 0 is the most significant bit? What does that mean? We don't negate the quotient, so that becomes 1, right? And then we don't add the mantissa since it's a 0. And then fourth, we did 1 and 0, and we add. And here's an interesting little trick, and this is the reason why I highlighted. If you figure it out before, right? Let's say you get 9 divided by 4 as your question, right? So this becomes 1, 0, 0, 1, and this becomes 0, 1, 0, 0, and your result is going to be 2 remainder of 1, right? So this means your quotient is going to be 0, 0, 1, 0. Now if you negate all of those, like it's the same thing. We had this. You go 1, 1, 0, 1. This is a useful thing to know because if you look at our flipped bits, right? This becomes 1, 1, 0, 1, right? These values in red happen to match the negation of the remainder. So if my advice to you on the exam, figure out the binary value of the result. And let's say you went through and you got 1 as your first bit. Okay, great. Second iteration, you get a 0 as your most significant bit. What does that mean? You made a mistake, right? So this is a good way, instead of getting all the way down to the end of the quotient and getting it to go, wow, I'm getting 13 with a remainder of 6. Where did I make my mistake? You can use this as a little trick to catch yourself at the exact moment you made your mistake. Okay. So, any other questions before we go to non-restoring division? So before we go to non-restoring division, what are some of the, what do you see, what do you think we would have to do in order to actually physically implement this? What do we need? So we have our inputs, and what actual arithmetic operations are we doing? Addition and subtraction, right? So we would have to perform a 2's complement, We have to perform a subtraction, and then we get a result, and then we have to have some sort of binary representation deciding whether or not we add, right? If we're doing this in VHDL, if 1, add, if 0, result is mapped to the previous value, right? You would have some sort of if statement in there. So you guys could actually implement this in VHDL if you wanted. Now, you would have to have 2 adders, right? For every step. So every step becomes 2 of n for your runtime, plus the shifting. Okay, so now let's go to non-restoring division. So the difference here is we're not going to restore every iteration. We're going to do something here at the end, though. There's a difference. So every iteration, so the loops, to put brackets here, would end here. So that's the difference. Same initializing steps as before. Same number of loops. Same thing, we're going to left shift the remainder, and the most significant bit of is the quotient. But instead of subtracting the mantissa every time, we're going to use that bit we popped off at the initial value. Remember back here, it was 0, 0, 0, 0, 0, and some 0 bit went away magically. For this algorithm, we're going to use that. So if the most significant bit of the remainder is a 1, then we're going to subtract. Else, if it's 0, we're going to add it. Right? And then we're going to do the same thing where we negate the least significant bit and the most significant bit. Now, after we do our 4 iterations, we're going to check if the most significant bit of the remainder is 1, then we're going to add the mantissa to the remainder. Now, why do you think we'd want to do that? Why would we want to add the mantissa if the most significant bit of the remainder is 1?
It's a sign bit, right?
Yep, it's a sign bit. So we have a negative remainder. So somehow we've gotten 9 divided by 4, and then we're going to get our correct quotient. We get 2, but we could potentially have some negative value. That if we restore the mantissa, it becomes the correct value of 1. And since in this case the mantissa would be 4, it would be negative 4. So it would be whatever value plus 4. So it would come out as negative 3. We'd have to add 4 and bring it to 1. So that's what our result would be. But we want this because we don't want a negative remainder to be calculated. So going back to our pros and cons, at the pros, for each loop, we're only doing 1 addition or subtraction every time, right? So instead of doing two additions or subtractions, we do that just once. So the loops go faster. However, we trade off, if you recall, now we're using the sign bit to do addition or subtraction, so now we have an add subtractor. So we're having 1, but as you guys recall from earlier in the section, add subtractors are a little more complicated, right? Additionally, when you're done with that calculation, you need to do a check and potentially do another addition here. So this would run faster, but there may be more hardware overhead. Does anybody have any questions on this before we go on to do the example question? People are still jotting stuff down, so I'll give you a minute.
The difference if it's 1, we subtract, and if it's 0, we're going to add. And that will ensure, by doing this, you're doing this trick that I showed you earlier about negating the bits of your expected solution, it'll still come out the same. So I want to state this before we do example 3.10. The homework will just be, homework 10 is going to be TGOs 3.18 through 3.20. And it's going to be example questions 3.7 through 3.10. So it's a 2 sign multiplication, sign restoring, restoring and non-restoring division. So here's the difference. We're going to do the same problem, 8 divided by 3 using non-restoring division. Initialize it the same as before. Again, we'd have the same value where we have the quotient here. It's going to be popped off. So now it's going to be 3. So the 1 is popped off of here. So it's initially this. It's popped off and becomes the least significant bit. So now the most significant bit is 1. Wait, I screwed this up. Do we pop off of 0? Damn it. That's every year. Forget to update it properly. Well, this year, bam. All right. Every year I look at that and I'm like, damn it. This is the year because it's wrong in the original slides I borrowed it from. So since we pop off a 0, we're subtract. So it becomes 1, 1, 1, 1, 0. Since it's a 1, same thing. We take this 1 and it gets lopped there to 0. We do not restore, so we left shift. We take the 0 bit here and it becomes the least significant bit, so that's this value. Since we popped off a 1, we're going to add, right? Add 3, this becomes 1, 1, 1, 1, 1. Most significant bit is a 1, therefore we negate and the least significant bit of the quotient becomes a 0. Third, we left shift. We popped off a 1, so we're going to add 3. This becomes a 0. It's the least significant bit. The most significant bit of the remainder. So we negate that and make that the least significant bit of the quotient. Left shift, we popped off a 0. So we're going to subtract. We get 1, 1, 1, 1, 1. Negate this and make it the least significant bit. Now, since the most significant bit of the remainder is 1, we're going to add the mantissa again here, right? So now this becomes, if you add these together, this becomes 0, 0, 0, 1, 0. So now we have 2 remainder of 2. So just to clarify, if the most significant bit is 1, you add the mantissa, else you're going to subtract it. Does anybody want me to go through this algorithm again?
I got a question. On
Yeah.
cycle 3, so we're adding the mantissa since we
Correct. I'm
popped off the 1 before, so we're just going to add the mantissa.
I'm scrolling up so that way the students in the back can see. So cycle 3, is this what you're talking about?
Yeah, and so we add the mantissa, so...
Yeah, we popped off a 1, so we add the mantissa, correct.
whenever I'm looking at it, for some reason why it's not adding up right in my head with what we got there.
Oh yeah, here's why. Let's do it. Because this carries. Get rid of this here.
Okay.
So start here. What's this value?
1.
Correct?
And then that's 0.
0, right?
Yeah.
So what's this going to be?
That one's going to be 0 as well.
And so what are the rest of these going to be?
Yeah, they're all.
Yeah, it'd be zeros. So that's how it works.
Yeah.
Yep.
I thought does the 1 not carry? Or
Yeah, no, it goes away.
it just goes away?
Yeah.
Okay. It gets outside of our.
Yeah.
Okay. That's what I was wondering.
Yep.
Can you repeat the homework one more time?
Yes, it is. Listed right here. 3.8 through 3.20. These are the 3 algorithms. Sign multiplication, restoring and non-restoring division, and then 3.7 through 3.10 are the 4 example questions that we covered today in class. Hey, does anybody else have any other questions before we dismissed? Okay, that's it. I will see you on Thursday.